Hello, this is chapter 4 review for chemistry. The big ideas of this chapter are the properties of light and the quantum model of the atom. So the cool thing about light is that it can act as a wave and as a particle. So in the electromagnetic spectrum, we see it acting as a wave. In the visible light spectrum, we have the colors you can see, and we have violet being the shortest wavelength at 400 nanometers, and red being at the highest wavelength with 700 nanometers. Also, in the electromagnetic spectrum, we see an inverse relationship between the wavelength and frequency of a wave. So, the shorter the wavelength, the higher the frequency, and you can kind of think about it logically if you were to have a graph of a wave. So with one period, the longer the period is, the less it would oscillate in a certain amount of time, and that is the definition of frequency. So if we have another wave function and it oscillates more frequency, so as a shorter wavelength, which is from here to here would be the wavelength, compared to here, if the wavelength is shorter, it oscillates more frequently, so the frequency is higher. A couple of equations we would use with relating wavelengths and frequency is C equals lambda times V. Lambda is the wavelength of a wave, and it must be in meters if you're using this equation, and that's because speed of light constant is in meters per second, so you must have unit cancellations. V is for frequency, and the units are 1 over s, or s to the negative 1. And c is the speed of light constant, which is 3.00 times 10 to the negative 10 to the 8th meters per second. And the second equation we have is energy is equal to Planck's constant times wavelength, or frequency, I'm sorry. So Planck's constant is 6.626 times 10 to the negative 4 joules seconds, and energy is in joules, and frequency is still in 1 over s, or s to the negative 1. So the quantum model of the atom. So the quantum model of the atom is basically how we arrange electrons in an atom. So in an atom, there are different levels of sublevels in which electrons will fill. So we have principal quantum numbers, which are the main energy levels, and those are denoted by an n. So there's a 1, which only includes an s, the s orbital. 2 includes the s orbital and the p orbital. 3 includes the s, p, and d orbitals, and 4 includes the s, p, d, and f orbitals. So the quantum number also dictates the number of orbitals in that energy level. So for in the first energy level, there is only one orbital, and the number of electrons in that main energy level would be denoted by the equation 2 times n squared. So in the first energy level, we can look at an example. So let's just use helium. So in that, so for the atom of helium, that has a quantum number of 1. So there's going to be one orbital, and that'd be the s orbital, and the maximum electrons for that energy level would be 2. And helium does have, in fact, 2 electrons. So with filling in electrons, we have 2 principles. So we have Aufbau's principle, which states an electron occupies the lowest energy level, that can take it. So electrons fill in order of increasing energy. 100 rules states that orbitals of equal energy are each occupied by a second electron, and all electrons in singly occupied orbitals must have the same spin state. So if we're looking at an orbital, let's just do the 2p orbital. All these electrons that singly occupy an orbital must have the same spin, which will be denoted by the same up arrow or down arrow. So we would not see something like this here. So electron orbitals. So electrons are the electron orbitals are broken into blocks. So over here and on to the left of the periodic table, we have the S block, and these are your alkali metals and alkali earth metals. All your transition metals will be in the D block, and some of your metals, nonmetals, and metalloids are in the P block, and these atoms down here are the F block. So orbital notation. So orbital notation, you denote all the orbitals that are there, and you show the spins of those electrons. So for example, if you look at carbon, we can see that carbon is in the 2p orbital. So that means we have to show the 1s, the 2s, and the 2p orbitals. So if we look at a period table, we can go down. So looking from the first period and going at all the atoms there, we see that we completely filled the 1s orbital. So we have our up arrow for that, the first one, and then down arrow for the second one. Likewise for the S for the second period, and we look at the S block there, you can see that we completely fill up both electrons. And then onto the P orbitals, we see that we take up 2. So this would be the orbital notation for carbon. Likewise for calcium, it would be pretty similar, but the only thing is that there is more orbitals that would fill up because calcium is in the 4s orbital. So we have the 1s, 2s, 2p, 3s, 3p, and then 4s. So likewise, the carbon we fill up are electrons, and calcium is the second atom in the 4s orbital, so we fill in both electrons. For chromium and copper, these are kind of exceptions. They're denoted a bit differently on how we would expect them. So I'm just gonna start drawing the orbitals. So we have the 1s, 2s, 2p, 3s, 3p, 4s, and 3d. So how we would fill this in, it's contrary to what we would think. So what we think it would fill in like this. However, this is incorrect because with chromium and copper, it's actually more stable for this electron over here to move to this 3D orbital, and it would look like this. And then similar thing happens with copper. So if we go on filling in the electrons for the atoms there, we would have the 4s orbital completely filled in, and have something look like this for copper. But again, it's more stable for this to be completely filled. So this electron over here would be moved down to the 3D orbital, and we would have something that looks like this. Electron configuration notation. So this is really similar to orbital notation, except if we do not show the spins of the electrons. So for carbon, again, we know it's in the 2p orbital. So we have the 1s, 2s, and 2p. So we know that carbon that fills up the 1s orbital, the 2s orbital completely, and then it only goes 2 in for the 2p. So it's just the same thing as the orbital notation, but instead of with the spins, it's denoted by the number of electrons that it will take up. For calcium, it's in the 4s. So we have 1s, 2s, 2p, 3s, 3p, and 4s. So we know that the s orbital is completely filled up. We know the 2s orbital is completely filled up. The 2p orbital is too. Same thing with the 3s and the 3p. And calcium is the second electron, or the second atom in the 4s orbital. So 2 electrons would be filled up. Likewise with chromium and copper, it's gonna look the same way as it did in the orbital notation. So we have 1s, 2s, 2p, 3s, 3p, 4s, 3, 3d. So that's orbital, the 1s orbital completely fills up. Same thing with the 2 orbital, the p orbital, the next s orbital, the next p orbital. But instead of this being a 2, this should be a 1. Instead of this being a 4, this should be a 5. And then same thing with copper. This should also be a 1 instead of a 2. And this would be a 10 instead of a 9. All right, noble gas notation. So noble gas notation and electron configuration notation are really similar. The only difference is, instead of writing out the entire number of orbitals, we go up to the nearest noble gas. So, for example, for lead, the nearest noble gas that precedes it would be krypton. So we would have krypton in brackets. And then we would fill in the 5s, the 4d. So we have 2 electrons that fill up in the 5s, and we have 1, 2, 3, 4, 5, 6, 7, 8 electrons that fill up in the 4d orbital. All right, for potassium, we look at the closest noble gas that precedes it, which is argon. So we have argon. You put that in brackets. Potassium is in the 4s orbital, and it's a first atom, so it's a 1. And iron, the nearest preceding noble gas, is again argon. So I made a silver there instead of argon, my bad. So we have the 4s orbital and the 3d orbital. So we would have 2 electrons fill up in the s orbital, and then we would have 1, 2, 3, 4, 5, 6 electrons fill up in the d orbital. That is all for chapter 4. Good luck on your midterms. If you need any help with chemistry, I have a friend that's up in the learning comments during second period, and he's really good with chemistry. So if you have a study hall that period, I would recommend you go up to the learning comments for some peer tutoring. His name is Ian Meyerhoff. He's really good with chemistry, so I recommend him. I'll see you next time.